Hello and welcome back to App for You. In the previous video, we just discussed about the polynomial curve fitting, and we concluded the video with a short introduction with overfitting, right? So we were introduced with overfitting condition. We saw what was actually the overfitting condition, and we basically introduced the polynomial curve equation, the polynomial curve. We just saw what was the equation of the polynomial, and we saw that for a higher order polynomial m equal to 9, the curve that was being generated by the model was passing through all the data points. Remember, the blue circles here are the training data points, and the curve that was being generated by the model was passing through all the training data points. What does it mean? It means that now for each point, you can see here the training value is equal to the predicted value, because the curve is actually passing through the point. So you can see the predicted value is this, and the training value is also this, right? For this point, not training value, the actual value. For this point again, for this point you can see this particular situation here, the actual value is this, and the predicted value is also the same, because they are lying on the curve. So this was leading to a training error of 0. Right, so this was leading to training error 0, and this is obviously a good thing. But what is the worst part? The worst part is while trying to bring a training error of 0, the model generated a curve which is very much different from the green curve. And remember, we had actually generated this data using the green curve and then adding some noise, and the objective was to come up with a curve which is very similar to the green curve, because the pattern followed by these data points here is actually the green curve. So whatever curve is being generated should be similar to the green curve. But here we saw, although the curve is passing through all the training data points and having a training error of 0, but the red curve is quite different from the green curve. Now, how do we basically control this overfitting, right? Because we know that this is leading to overfitting. Why? Overfitting means wherein the curve basically deviates from the generalized curve, right? Because the actual curve is green, and we were expecting the red curve to be similar to the green curve, but here we can see the red curve is very much different from the green curve, although the training error is 0, which means the training error is 0, but the testing error is very high. We just introduced these things in the previous video. Now, how do we control this overfitting? We saw one technique of controlling this overfitting was to increase the number of data points. Here we were dealing with n is equal to 10, and you can see the red curve is oscillating too much. But when we increase the data points from n equal to 10 to n equal to 15, we saw that the curve basically tries to come closer to the green curve, right? To look similar to the green curve. It tried its best to look closer to the green curve, which means the model is trying to basically capture the pattern. Again, when we increased n equal to 15 to n is equal to 100 further, which means when we are increasing the number of training data points, we see that the red curve, which is actually the curve that the model is trying to generate, becomes very much similar to the green curve, you can see, which means this model here basically has successfully able to capture the pattern. And once the model has successfully been able to capture the pattern in the data, now the testing error will be very, very low. And that is what we want, right? You can see. So another technique in this video that we are going to discuss is how do we control overfitting using regularization. So in order to introduce you with the regularization thing, let us first of all see what regularization actually is. So one technique that is often used to basically control the overfitting phenomenon is basically the regularization. So what happens in regularizations? It involves addition of a penalty term to the error function, right? So remember, this entire term was the error function, right? This was the error functions that we had basically discussed in the previous video. Now, in order to control overfitting using regularization, we will add an additional term, which is lambda by 2 and this w square, modulus w square. Now, what is this actually? This is actually the penalty. This is a penalty term. This penalty term will basically take into account and reduce the overfitting. Now, how does it reduce the overfitting? Remember, we discussed in the previous video that the ways in which you can basically create the ways in which the red curve, which is the curve which the model is trying to generate, that is the pattern that the model is trying to learn. The red curve should be similar to the green curve, which is the actual distribution of the data, right? Data points. Now in order to do this, we saw that when we have a lower order polynomial, that is m is equal to 0, the red curve was very much dissimilar from the green curve. Even for higher order polynomial for m equal to 9, the red curve was not similar to the green curve, but it was very much different, we can see here. But for m is equal to 3, we saw that the red curve was looking quite similar to the green curve, which means it is actually trying to capture the or follow the actual pattern in the data. Now to make the red curve look similar to the green curve, that is to actually capture the pattern hidden in the data, we understood that the order of the polynomial should be optimal, right? We should have a good order of polynomial, neither too low nor too high. This was one technique. But what if I say that, okay, I just want to have a higher order polynomial of m is equal to 9, and now what are the techniques using which this red curve, now in this situation where m is equal to 9, remember now I am not going to, we know that if I make m is equal to 3 or 4, the red curve will be looking similar to the green curve, right? But now what if I say that we just want to have a higher order polynomial m is equal to 9. Now in this situation, if we want to make this red curve look similar to the green curve, the only way is to update the coefficients. Right? What are the coefficients? Remember the polynomial equations y x comma w is equal to w0 w1 x1 and so on till mth order. That polynomial equation, these terms w0 w1, these weights, if we try to modify, then this red curve can look similar to the green curve. Now how do we modify these weights? We introduced in regularization the penalty term. So what will the penalty term do? Basically, we can see here, this will basically try to update the weights coefficients accordingly. So the technique that is often used to control the overfitting phenomenon is regularization, and which involves addition of a penalty term to the error function. So this entire thing was the error function. We just will add a penalty term, this term, right? The simplest such penalty term takes the form of sum of square of all the coefficients. Remember this term here, basically this term is nothing but the sum of squares of all the coefficients, w0 square, w1 square, so on till wm square. The sum of squares of all the coefficients will be used, and this lambda will basically give us the relative importance of this penalty term in this error function. What is the, or you can see a sort of weight, right? How much penalty should be applied to the error function. So accordingly the coefficients will be adjusted. Now this particular case of quadratic regularizer is also called ridge regression. And remember, in neural networks, when we learn deep learning in neural networks, we will also come across this error function again, and in that case this approach is basically known as weight decay. So we will see how this regulation has actually helped to reduce overfitting in the following slides. So this is one of the table that was that is shown. So here you can see that what was the error function actually. The error function was, this was the error function, right? Just remember this was the error function, and we are adding some penalty term here. Now focus on this lambda, which basically gives the relative importance of this error penalty term with respect to the error function, right? Now we will try to modify this lambda, either increasing and decreasing, and we will see how the overfitting is actually being controlled by increasing or decreasing the value of lambda. So what we do here is basically we see that for m is equal to 9, remember we were just sticking to the higher order polynomial. We are not going to modify m now, but we are trying to optimize the coefficients, keeping the polynomial of order m equal to 9. So for m equal to 9 polynomials with various values for regularization parameter lambda, what do we see? When ln lambda is equal to minus infinity, ln lambda is equal to minus 18, ln lambda is equal to 0. So here what we are doing, we are trying to increase the value of lambda, right? This is the very low value of lambda, bit higher value of lambda, and the value of lambda here is very high. So what we see is, for a lower value of lambda, wherein this situation basically means that the regularization is almost 0. This means no regularization. So you know that when you are doing no regularization, when no regularization is done, then the model is here basically for m equal to 9, the graph is overfit, the curve is overfitting. You know that I am talking about m equal to 9 without regularization. Remember, ln lambda equal to minus infinity means no regularization condition. So if you have considering a curve of m equal to 9 and you are not doing any regularization, then it is clearly an overfit condition, because you know what was the curve actually looking like. But now I increase the value of lambda, and now ln lambda equal to minus 18, you see the coefficients have drastically reduced, which means the curve is trying to reduce its coefficients, either increase or decrease, but adjust its coefficient values, and that will basically modify the curve. On further increasing the value of lambda, you see the values has further decreased. So what is the point to be noted? That for ln lambda equal to minus infinity, this corresponds to a model with no regularization. That is the graph at the bottom right, we will be seeing this graph. So if you have ln lambda equal to minus infinity, it means no regulation conditions, right? And we can see the value of lambda increases, the typically magnitude of coefficient gets smaller. So it is obviously clear from this diagram only, right, that as the value of lambda is increasing, the coefficients here, these are the coefficients, you can see W0, W9. You are see in all these conditions we are having 9 coefficients because we are considering the polynomial of m equal to 9. We are not trying to modify the m. For this value of m equal to 9, we are trying to modify the coefficients only by adding some penalty. Here ln lambda was minus infinity, here ln lambda was minus 18, here ln lambda was 0. This is too high value of lambda, this is too less value of lambda. This is the optimal value. We will see that this particular situation here will give us a good curve. So we can see that this diagram here, it is clear from the fact that here m is equal to 9. So this was the condition where the model was overfitting, right? Now this curve, red curve, is not looking similar to the green curve. We are trying to have m equal to 9 only, and just by adjusting the coefficients we want to make this red curve look similar to the green curve, because the green curve is the actual pattern of the data and red curve is being generated by the machine which is trying to learn the pattern. So when we are putting an ln lambda is equal to minus 18, when we are having a penalty term, when we are penalizing the coefficients by keeping the lambda value, ln lambda value as minus 18, we can see that this curve only has converted itself to this curve, which means the coefficients have adjusted itself to learn the pattern. On further increasing the value of ln lambda to 0, you see again the red curve has become sort of linear, and here the error is too high. You can see the error is too high. So many errors are here. So here also testing error will be high, right? Here you can see testing error will be low because the model is actually learning well, and here also the testing error is high, which means this ln lambda equal to minus 18, we want to have a the lambda value such that it is neither too low nor too high. How do we see? You can see at this point, this is the root mean square versus the ln lambda plot. So it is very simple to understand. Remember, root mean square will be 0 at this point, right, when ln lambda is very low. Remember, when ln lambda is equal to minus infinity, we saw that for this is for m equal to 9, okay? This is for this polynomial curve. So when ln lambda is equal to minus infinity, which means when it is very low, which means you are not applying any regularization. If you are not applying any regularization, what is the condition? It is overfit. And what happens in overfit? The RMS value for training data will be equal to 0. ERMS will be 0, root mean square, and the testing error will be very high. You can see for m equal to 9, when the ln lambda is very towards minus infinity, the this is the blue curve is the training error, okay? Training error is 0 and the testing error is very high. Now as you increase the value of lambda to minus 18, you can see here at somewhere here the training error is very low, right, and the testing error is also drastically reducing. You can see reducing. It is remaining same for some time. Again, beyond certain point, when you increase ln lambda further, again the training error also increases and the testing error also increases, isn't it? So this is the pattern that we can observe, that how the regulation can actually be done to modify the coefficients of the polynomial curve. And I hope this curve is very clear what it actually means. You can see for here basically the ln lambda is equal to minus infinity, and in this case we know that the model is overfitting. So if it is overfitting, the training error will be equal to 0, almost 0. You can see the training error is 0 at ln equal to minus infinity, and testing error is very high. Overfit condition. Again, by increasing the value of lambda, when we are trying to penalize it, we can see the training error is basically slightly increasing, which is good because it is trying to generalize it, right? If you want to generalize it, you will have to accept little bit of training error. But here again you can see that testing error has drastically reduced. So this is the good thing. For some time the training error, testing error remains same, and then again after increasing ln lambda further, we see that the both training error and testing error increases. So this is the reason that we basically want, right? So I hope this video was helpful. In case of any doubt, please feel free to put it out in the comment section, and just like, share and subscribe. This is all about how the coefficients adjust themselves to reduce overfitting by using regularization, right? So I hope this video was helpful. Thank you.